start off doing something a little different. Normally, I do a bit of magic, but for reasons I won't bore you with, I'm not able to do it this time. So what I'd like to do instead is just a little experiment about user experience. Is anyone wearing a watch? It can be a smartwatch or an analog watch. Would you mind standing up if you're wearing a watch? If it's a fitness tracker, it's probably not going to work, but a watch of some kind is pretty good. So what I'd like you to do is hold your hand with your watch on it in front of you, and then place your other hand over it so that you can't see it. Now the first thing I'm going to ask, without looking at it, which is why your hand's in front, do you know whether it's an analog or a digital watch? Which I'm hoping most of you do. Even a smartwatch, you choose your watch face. And if it's a smartwatch, please, it's the face that when it's fully awake, not your sleeping face. So does anyone not know whether it's an analog or a digital watch? That's good. So everyone at least knows that much. Because you look at your watch a lot, and it's a conscious choice for most people whether they prefer analog or digital. So it's usually a choice you make when you buy your watch or choose your watch face. So for those that are using a digital watch, would you sit down? So, but if you've got an analog face, it can be a smartwatch with an analog-like face. But so there's still a few of us still like an analog watch face. So still with it covered, the digits on it, can you tell me, or do you even know, are they Roman numerals? Are they Western numerals, so the letter 3 or an III, or no digits whatsoever? Does anyone not know? Is anyone thinking, I need to look and check? The laughs are saying a lot here. This is a strange thing about UX. You look at your watch how many times a day to look at the time. You chose your watch yourself or the watch face, but you can't remember what the digits are. And likewise, I bet if I was to ask you about the ticks that mark the minutes, do you have them for every minute, every 5 minutes? Are there ones for 15 minutes longer than the 5 minutes and shorter and longer again than the single minutes? These are all details that we just don't see anymore, even though we look at it a lot. And so I would like you to look at your watch and remind yourself, do you have Roman numerals, digits, and also look at the ticks. So now cover up one last time. So you've just looked at your watch in great detail. Who that still stood up can tell me what time it is? And again, this is another interesting thing about user experience. You looked at your watch and you saw some information, what you thought was going to be important, but you didn't look at the time. And that's your primary reason for buying a watch. And this shows why user experience can be controlled by us as developers and designers, because we can lead the user to the right piece of information through creative use of user interface. So thanks for your help. A little, just a distraction before we get into the main thing, but I hope it was thought-provoking at least. So, yeah, this is me. I'm, let me firstly get my clicker working. Yeah. So I'm this fella. I'm not going to give you all the intro. The only thing I'll mention on this slide is my Twitter handle is Mark I. Allisson. That is an I there, not an L. If anyone follows me on Twitter, I will be live tweeting during the presentation so that there'll be links to related articles and information if the tweet's working, which sometimes it doesn't, but hopefully you'll get some live tweets throughout. So we're going to talk about vector drawables. I love vector drawables. I just love playing with them. They are a constant source of excitement to me using them. Anyone here not use vector drawables at all? So everyone's using them. Wow, that's pretty good. So just a quick recap. They were introduced in API 21, which is Lollipop. So they've been around a while. Actually, initially, Android Studio was pretty awful with its vector drawable support, but it's got a lot better. It's not something that people have shouted about an awful lot, but you can import SVGs into Android Studio directly using the image vector import tool, and it's really, really good. It really does convert the vast majority of SVG files you might have. And we got a support library from 23.0, or 23.3, I think, 23.2 even. The support library gave us vectors back to, I think it was API 14 when it first came out. So there's no excuse for not using them. But there were some things that have been added since. And that's really what we're going to talk about today, some of the things that have been added since the initial release of vector drawables at API 21. And one thing that we'll see is use the support library. There are some caveats to it. The support library generally won't be as performant as the native library you use because it's having to do stuff that it can't get to at the framework layer. It's not quite as efficient, and is having to have some optimizations to work around on older devices and things. But there are a number of bug fixes and new features that have gone into the support library. So it's worth using. It really is. So the first thing we're going to talk about is fill windings. Does anyone know what fill windings are? No hands, is that? Wow. Okay, that's good. It means you might learn something. Fill windings are the rules by which a shape is filled. And I really fell foul of the one time when I had a shape that was a bit like a donut, but it wasn't actually being drawn like a donut. So here we have two donuts that have different fill windings applied. And you can see one has a hole, like you would expect in a donut, and the other one doesn't. So let's look at the code that draws these. Now, these two vectors are almost identical. And if we actually overlay the code, you can see the only thing that's different between these two examples is this fill type. So the actual paths themselves that make up the donut are identical, but this fill type is different. One of these is non-zero, and the other is even odd. And these are what are called fill windings. So let's firstly take a look at even odd. Before we go into it, let's just discuss how these paths are constructed. So we have two circles. So in the path data, we'll do a little bit of path data later on, so don't worry about what this path data actually does, except that it draws a circle, and the important thing for the purpose of fill windings that will become relevant later on is that it draws the circle in an anti-clockwise direction. So that is the outer circle. The next part of the path is an inner circle, and that is also drawn in an anti-clockwise direction. And so that is what comprises the two components that make up this compound path. The fill winding or fill rule is the rule by which we determine if any given pixel is painted with the fill color or not. And these rules are the fill windings. So for the even odd rule, what we do is let's pick a point. For the sake of argument, it'll be the one dead center, but it could be any point within the inner circle for this piece of the example to work. And what we need to do is draw an imaginary line from that point to the edge of the canvas. And it can be any edge of the canvas. It doesn't really matter which, and I'll explain that as we go. So if we start drawing that line, we need to count how many times we cross a path. So in this case, we're crossing once, and then again, twice, and then we hit the edge of the canvas. So we've crossed the path twice. And what's important here is whether we cross the path an even number of times or an odd number of times. If we cross the path an even number of times, then we should not paint the pixel with the fill color when we fill the object or fill the shape. If we cross an odd number of times, then it's deemed to be inside the path, so it should be painted. So in this case, if we pick a point between the two circles and then draw an imaginary line, we cross an odd number of lines because we cross once. And what I was saying earlier, it doesn't matter which direction we go, is if we go the other direction here, you can see we actually cross 3 times. So it's still an odd number, so we're still inside the path. And so if we then fill that shape using the fill winding even odd, we get our donut shape, which may be what we wanted. The other type of fill winding we have is the non-zero rule. Now this is where the direction of the path comes into it becomes important, because we do exactly the same as before. We draw an imaginary line to the edge of the canvas, but every time we cross the path this time, we look at the direction that the path is traveling when we cross it. So it's a little like crossing a street. The traffic, if it's a one-way street, the traffic will always come from one direction. But then we could cross another street where the traffic is coming from the other direction. And that's what's interesting here. Every time it crosses in one direction, we increment the counter. But when we cross in the other direction, we decrement the counter. And so here, we've crossed once in one direction, we increment. We cross the second path in the same direction, so we increment again. So we get a count of 2 by the time we hit the edge of the canvas. And we fill everything within there because we're always crossing the paths at least once anytime we're within the outer circle. And this is what caused me a problem one time. We had a shape that was just not filling correctly, and it was because we had a non-zero rule being applied, and the paths were going in the same direction, and so it was filling the center of the shape rather than leaving it empty. So the way this got fixed was just by reversing the direction of one of the paths. So now the inner circle is being drawn in a clockwise direction and the outer circle in an anti-clockwise direction. And so this time we cross the first line, it's going in one direction, we increment the counter. Cross the second time, we decrement the counter, so we're back to 0. And that's what non-zero means. If it's non-zero, it's inside the path, but if it's 0, it's outside the path, so it doesn't get filled. So just by changing the direction of one of the circles, we actually get our donut. So by using the non-zero rule, we can actually get both behaviors just by changing the path subtly. And the reason this used to be far more important than it was is when vector drawables were first released in API 21, they only supported non-zero rule. There was no support for even odd. So you had to do this stuff in order to fix it. And I happened to have met the guy that worked on vector drawables, who left the team before they actually released vectors in API 21. He was fully aware of this. He had all the wiring in place and had a to-do put in the code to actually just hook it up, because the support was in Skier, the underlying graphics library that Android uses for this stuff. And all it needed was wiring up. It was a 30-second job, and it never got done. And he was so annoyed, and it continues to rankle him. He was actually at a conference I did where I gave this talk, and he was cringing in the front row. And I won't name him. I wouldn't want to embarrass him. But it was the one thing that really pained him about leaving the team, that this never got done. They were actually added in API 24. So from API 24, you have this fill type attribute where you can actually specify. So if you see weird rendering stuff, it might be worth playing around with your fill types, and you might find they just automatically work. And it was added into support library 26. So can you guess what's coming next? Use the support library. So the next thing we'll cover, this isn't specifically to do with vectors. This is an oddity you can use in any XML files on Android. But it is particularly useful for vectors, particularly animated vectors, for keeping your code readable and maintainable. And it's inline complex XML resources, which is a real mouthful. And what it is, it's a way of combining multiple resource files into one. So here, for example, we have a vector. This is a square. If we wanted to animate this, we'd have to create 3 separate files. So we'd have an object animator, which actually performed the animation. In this case, this is just going to just fade the alpha in and out. We have the vector itself, and then we have our animated vector, which is a mapping file that maps the elements in the vector drawable to the individual animators. And this can get quite tricky to maintain when you've got these 3 files to look at to comprise a single animated vector drawable. Inline complex XML resources allow us to actually combine these into a single file. And they work like this. And you can interchange them. So on the example here, you can see that here I'm using a standard target, whereas the main block of code, we're actually embedding the vector inside the animated vector. And how this actually works is down to adding this AAPT namespace initially. Now, some of you may have heard of AAPT or seen things when your Gradle builds are running for hours and hours. You tend to see these things. AAPT is Android Asset Packaging Tool. And it's the bit that's responsible for compiling up your resources, converting them into binary, and packaging them up ready to go into your APK. And this technique actually just uses that process to be able to inline your resources into a single file. So for example, you could do things like embedding a style directly into a layout and stuff like this, or actually even, say, a selector drawable into a shape or whatever. In this case, we're going to use it as a vector. So you first need to define the AAPT namespace so that you get these nice extras, and it triggers AAPT to run on this file. Next, we create this AAPT attra element. What this is doing is exactly the same as this one here. So you can see the name is Android Drawable. And what it's going to do is actually embed a drawable within here. So normally you would have a drawable attribute on the animated vector, but this is actually declaring it inline. So what's going on in here is exactly the same as what happened in our external vector file, but just by using this attra here, we're applying an Android drawable attribute to the parent element, and that embeds that there as if we put in a drawable resource ID. So it means we can keep all the components within the file, and that's literally just the same as we copied in from the file. So these were added in AAPT 2.2, which, given that I'm sure most of us are running Android Studio 3.x now, everyone's got access to. They're essentially a way of bundling multiple resources into a single file, but they get broken up during the build. So what AAPT does is it sees this in line, it strips it out into a separate file, and then puts the reference back in. So what's actually getting compiled is exactly the same as if you did it in 3 files, but it will just break it up so that your source contains grouped together nicely so you can read it and understand it. But then at compile time, it's exactly the same as if you'd done it in separate files. And there is a cost to this. If you embed the same vector in multiple different files, it will split each one out separately. So you will get lots of copies of that same vector drawable. So sometimes it is worth considering whether readability is better than a smaller APK, because there is a knock-on, and it has very limited auto-suggest. It may be improving, but whereas if you're editing a vector drawable XML file on its own, you'll get auto-suggest for element and asset names, but you won't if you're doing it inline. It's really not got there yet. And as I just mentioned, we can bloat our APIs if we just do this everywhere. So it's worth being aware and understanding the costs of using this. The next thing, gradients. Designers love gradients. And I can remember having lots of discussions with designers who would give you these nice designs and say, oh, I've got this SVG file, can we use this? And then I'd tell them, sorry, Vector Drawable doesn't support gradients. And their faces drop. I can't use gradients. Fortunately, we can now cheer our designers up. And we like designers. They do nice things, and we work well together. So we can now tell our designers, yes, you can use gradients. And so they'll go out and put gradients on everything. And then we'll say, yeah, it's maybe not great to do it everywhere because that's not great for performance, but then we find a happy medium. So gradients are a relatively new addition to vectors. They were the really big thing that was missing from vectors for a long time. And we'll just cover the basics of what kinds of gradients we have and how we can use them. So the simplest form is a linear gradient. So this starts at one color at the top and transitions to a different color at the bottom. These are quite easy to do. We first create a gradient element. We give it a type of linear. So, yeah, we know this is a linear gradient because we just explained what a linear gradient is. For a linear gradient, we need to give it a start position and color. So in this case, the start position is 0, 0, which is at the top left, and the start color is this light green. We then give it an end position and color. And so in this case, it's a darker green. Actually, all I'm changing in this example is the alpha. So it's just changing the alpha of the gradient. And that's why we're getting these two shades. But the end position is 0, 100. So it is directly below the start position. So we draw an imaginary vertical line. And it's the direction of that line that determines the direction that the gradient will flow. And we could actually move this anywhere within the shape, or even outside of it, these 2 points, as long as they're directly above each other, the gradient won't change because the direction of that line isn't changing. If we change the end position, so it's the bottom right corner rather than the bottom left, then we'll get a diagonal gradient like that. So just by changing the direction of this line means we can completely control the direction of this gradient. So the next main type of gradient is a radial gradient. A radial gradient starts at one color in the center, and as we move away from the center, the color changes to a different value, a different color. And we implement this in much the same way. We have a gradient object. We give it a type of radial. And then rather than having a start and end point this time, we firstly define where the center of the gradient is. So this is where we're going to start rendering from the start color. And we give a radius. So the radius is the distance over which it's going to transition from the start color to the end color. In this case, we've drawn a circle that fits entirely within the box. So what you'll notice is these corners actually aren't changing. They're all at the end color because they fall outside the circle. And this is the thing about radial gradients, is they don't fill the shape that we're actually filling. They will be a fixed size. So you can add little highlight points and things like this by making small ones. Just by changing the gradient radius to 70.71, which if you do a little bit of trigonometry, you can work out, this actually expands the circle so that it touches the four corners. And so then we'll get a smooth gradient to the edges, and there will be no flat block of color in the corners. But it means we won't actually transition to the end color in these midpoints because the edge of the circle is actually out here somewhere. So you can quite easily control how we render these. The final kind of gradient is a sweep gradient. So a sweep starts at one color, and then we sweep around the middle. And every time we move the angle, for each iteration of the angle around the center, irrespective of how far from the center we are, we will slowly transition towards the end color. So we start here with the light color, and as we travel around in a circle, we gradually transition towards the dark color. And these are even simpler still. We firstly tell it that it's a sweep gradient. Oh, sorry about that. I accidentally, right. There we are. Once again, so we declare the type as a sweep gradient. We give it the center just like we did with the radial gradient, which is just determining this point, the bit around which we're going to perform the rotation. And then we just give it a start and end color. And it doesn't need any more information than that to be able to render this kind of gradient. But having that stark start and end edge isn't always what we'd like to do. It might be nicer to do something maybe more like this, where we actually start at the light color, we hit the dark color halfway through, and then we come back to the light color again. And that's easy to do as well. And this applies to all of the gradient types we've covered. You can add a number of stops within the gradient, so you can go through a range of colors on the way. So you could do a full 360 color wheel using this technique if you wanted. And the way we do this is where we had our start and end colors before, now we replace them with these items. So we can declare as many items as we like in here, and each of these items represents a color stop within the gradient. So this first one gives us our light color with the alpha set to 0 and at offset 0, which means this is going to happen right at the start. And this offset range is from 0 to 1, and it's a floating point value, so you can have any value from 0 to 1 as your offset. The second item is at 0.5, and we're going to the dark color with full alpha, fully opaque rather than transparent. And then when we hit 1, we're back to the light color again. So that's how we get this light to dark and then back to light again. And you could add many more of these stops if you wanted. And as I said, they work with the other gradient types as well. So you could have a radial that came out through various different colors, or a linear that went through a couple of different colors as well. So in summary, for gradients, they were added in API 24. Here's a gotcha. Sweep gradients are not supported by SVG. They are supported in tools like Sketch. So what you might find is if you get a design from a designer that has a sweep gradient in it, he will export it, or he or she will export it to an SVG file. You'll import it into Android Studio, and it will be no fill. There will not be a fill specified because SVG, the intermediate format, doesn't support them. It's not a failing with Sketch or any of those tools. It's not a failing with Android Studio because it's just doing what the SVG is telling it. It's actually just an omission within SVG specification itself. So if you ever see a sweep gradient or you see a gradient go missing as you import a file, check the SVG file, make sure it's there, firstly and foremost, and the chances are it could be a sweep gradient that's gone astray because of that problem. It's not difficult to put them back in manually once you understand how to use sweep gradients, but it's just something you need to be aware of. And thanks to Nick Butcher, these got added to the support library. He showed me a pull request that had been outstanding for about 3 months. He was telling me how he was nagging people to try and get it merged, and eventually it did. So they are now in the support library, so there's no excuse. We can really keep our designers happy. We don't have to make them cry by saying there's no support for gradients in here. So, come on, join in. Thought we'd get there in the end. So, there's been a fair bit of dry theory. And when I first put this presentation together, I worked day and night on it. So let's do something a little lighter just to finish the session. And we'll just do a worked example of how I went about creating this animation. This is an animated vector drawable. And looks really, really complex. There are a couple of tricky bits to it, but when you actually break it down into its components, most of them are really, really easy to understand. And that's one of the key things about animating vector drawables. Layering up little different, very subtle and easy to do things can actually create something that's far more complex and far more interesting visually. So let's break this down into some components. So we start with the background, which is a square. When the animation was running, did you notice that the background was changing? Some might have, some might not, but the background was actually changing from day to night. And this was just because we used an object animator that was changing the background color from a light blue to a dark blue. So day to night, the sky changes color, and that's all we did here. again, it might not have been noticeable because there's a bigger animation going on in front with the sun going to the moon. But nevertheless, it was still adding to the overall animation because it was adding a depth to it, it was adding a reality to it. And if you didn't notice it, it was because it seemed and felt natural. And again, that's an important part of getting really good organic feeling animations, that they feel natural. So the next thing is we draw a yellow line. This is about one of the simplest things you can draw in a vector drawable. And we can animate this by using a trim path. Every path element in vector drawable, you can apply a trim path to. The path is the entire line, and the trim path controls just a portion of it being drawn. So in here we can see the values of from and to are 0 and 1. And it's a trim path start. So we're only drawing the first part of the line. If we draw 0, it's going to draw none of the line at all. If we draw a trim path of 1, it will draw the entire line. But if we give a fractional value between 0 and 1, it's going to draw a portion of the line. So by animating the trim path, we can get this effect where the line seems to draw and undraw, just because I've got it on reverse for the sake of the example. So here we have a line drawing and undrawing, and the background changing color. The other thing that we do, and again, this is a subtle thing, we then change the stroke color from our yellow color to a gray. And sorry, I'm totally lying here. That from color is totally wrong. All we're actually doing is changing the alpha here. So yeah, my code is wrong here. I apologize for that. I will show you how you can get the source of this later on. So don't believe this, but believe the real source, because that's sort of right. But all we're actually doing is changing the alpha of this. So it's fading out as it's drawing. So again, here we can see the three things happening at once. We've got the background color changing, we've got the trim path, and then we're changing the alpha. So as this line is closing, it's also turning transparent, so it's beginning to disappear. But that's a line. That doesn't look at all like our sun turning into the moon. So how we do that is we first shrink this line, and then we duplicate it. So we've now got 12 of them. And if we run the same animations on each of those lines, we can now perform a little rotate. And by just doing this little 30-degree rotation, we can see how all these lines are just rocking backwards and forwards. We can then do a scale. And I'm just showing the X scale here, but we're doing exactly the same thing for a scale Y. We're expanding the size of this from 1, which is its actual size that we're rendering, to 1.4, which is a bit bigger. And by adding this to the rotation, we're sort of getting this grow and shrink as we draw this. And so then if we apply the trim path and the color changes to this, this is how we're animating the rays of the sun, sort of seeming to melt away as we transition to nighttime. So there's nothing really complex there. There's a trim path, there's some rotation, there's some alpha, there's some scaling, but layering them all up gives you quite a complex effect, but made from very, very simple components. So when we come to animating the sun and the moon, that's a little trickier. And here, I'm going to have to rush through this because we're running a little short on time. So apologies if this isn't quite as clear. But we're going to draw the sun. First, we move. That's what the M command does. So this is all SVG path data, which is what our path data in our vector is comprised of. The move command moves the current drawing point to a given point on the canvas without actually drawing anything as we make that transition. Next, we draw an arc. An arc is a section of a circle. And these are a little complex, so please try and bear with me. I'll try and explain it as best I can. The final two parameters are the x and y coordinates where we want to finish drawing the arc. So the move moved us to this point, and we're going to draw an arc to this point. And that's what the last two parameters do. The middle two parameters define the radius of the circle that we want to draw, or it could be an ellipse. If we had two different radii, they would be a different x and y, so we could get an oval or something like that. So if we were to draw a circle of that radius around each of those points, we will see that there's actually 2 points where they intersect, and that's these 2 points here. They are the centers of the only two circles on that canvas that can be circles of radius 49 that pass through both the start and the end point. And so they are those two circles. And the remainder of these middle attributes really control which part that we're actually going to draw. So this first 0 here is which of these circles we're going to draw. So we have two circles here, this one and this one. If we set that to 1, it will actually draw this circle. If we set it to 0, it will draw this circle. And actually, I missed out that the first 0 there is actually the angle that we're going to rotate through. We're not rotating anything here. We could rotate the whole lot if we wanted to, but we're not. The final middle digit is which section of this circle we draw. So if we set this to 0, we'll draw the shortest section between them. If we set it to 1, we'll draw this larger arc, and that's the bit we're interested in. So this is the bit that's common to both the sun and the moon. Now, to draw the final bit, we could draw another arc, but that would be difficult to animate. So what we're going to do instead is draw a cubic Bezier, which is denoted by the C. A cubic Bezier we cannot create a perfectly mathematically correct circle using cubic Beziers. We can get a close approximation, and as long as it's close enough to fool the human eye, that suits us for this purpose. So that's what we're going to use. A cubic Bezier uses two control points. So this is the current drawing position. That's where we finish drawing the arc. The final two parameters, again, are the end position. So that's where we're drawing our cubic Bezier to. And the middle two sets of coordinates are two control points. So this one is this control point. This one is this control point. If you've used a graphics drawing package, you'll be familiar with these and how you can move them to control a curve. If you're not, the simple mathematics of how this is calculated is, as we're drawing this arc from there, or this Bezier, I should say, it's not an arc, from here to here, as we leave this point, we're going to be moving directly towards the start control point, and the end control point will have no effect. But the more we travel, the less effect the start control point will have, and the more effect the end control point will have, and so it will start pulling us back so that by the time we hit the end point, we'll be moving directly away from the end control point and not be affected by the start control point. And so we get something like that. This is the clever bit. We don't need to animate anything there apart from the control points. And if we move those, just with 2 path animations, that's how we change the shape from the sun to the moon, just by pulling that in. We can then change the color by going from yellow to a silver. Then we can apply the same rotation as we're doing to the rays, and that's how we get to this final full animation. So sorry I've had to rush it a little bit, but I'm out of time. So I will just, before we wrap up, preempt one question. If no one has seen me speak before, no, I'm not going to release the slides. I'm really sorry, but I know what you're thinking. Why aren't you going to release the slides? There aren't any slides. I don't have any slides to release. The software I'm using here, it's a custom Android app, which is running on my Pixelbook. All the slides are actually made up using Android layouts. The animations you're seeing on screen there are real Android animations rendering in real time. And all the drawables you've seen on the screen are actual animated actually vector drawables. The gradients were actual Android gradients being rendered. There's a blog series that explains a little bit about how the app works that I wrote many years ago, but when I first did a presentation using this software. And hopefully those that have been following on with the Twitter stream, did the tweets work? Yes. So anyone that was following the Twitter stream should now have got a link to the blog posts that detail how the app works. And it's open source. There's a light version that I've released which has all the presentation slides in it that, again, you should have got on the tweet if you were following. It's available on GitHub. It's not the full version, so it hasn't got stuff like the live tweeting and stuff in there, because I really don't want to release my Twitter API keys to the general public, and everyone starts tweeting as me, which is great. But it's there, so feel free to have a play with it, look at it on GitHub. All the animations are in there. So where I pointed out there was a bug in the code, if you look at the one on the GitHub repo, that will be right, because that's what was actually rendering on the screen there. So that's really it. I hope you've got something good to take away from this. I hope you go and have a play with some of these stuff, because it's really good fun, and there's nothing finer than getting a really, really great animated vector going and thinking, wow. Sometimes you can just amaze yourself with what's possible. Enjoy it, and enjoy the rest of the conference. Thank you. So I don't think we're running over, so we haven't got time for questions, but I'll be around. I've got some swag. I've got some styling Android pins and badges, so feel free to stop and chat to me, and I can answer any questions in person or just